Hi there, everybody. Welcome to another Chem Complete lecture series. And in today's lesson, I would like to finish up with one additional practice problem on how to determine equilibrium concentrations using the square root method. So I first went over this in a couple of lectures back, and I will leave a link to that in case you're confused as we're going along with this practice session down in the section below where the description would be. So go ahead and check that out if you're not familiar with how to use the square root method or what allows you to use the square root method. And other than that, this is going to be the last practice problem we do on the channel regarding the square root method, and then we're going to move on to the quadratic equation technique. So that is what we are going to look to cover here today. Okay, so just a brief reminder regarding what ICE calculations are referring to. ICE calculations refer to a table or some sort of a chart that you set up in order to determine equilibrium concentrations. And there's three main components. There is the initial concentration, which is normally going to be given in the problem itself. There's the change in concentration, which we will represent using a generic X placeholder for change in concentration as we are headed towards equilibrium. And then obviously there's the actual equilibrium concentration itself for all of the different chemical species. And that's usually the goal of most of these problems. You want to determine the equilibrium concentration based on the initial concentrations and the information given in the problem. So you can see I've got an example here in which carbon monoxide and water vapor are going to react and go into equilibrium with carbon dioxide and hydrogen gas. So the problem here states that a reaction mixture initially contains carbon monoxide and water vapor at a molarity of 0.110. So what this problem is looking for is for you to find the concentration, the molarity, of carbon monoxide, water vapor, carbon dioxide, and hydrogen gas at equilibrium if the KEQ is 102. So that is the equilibrium constant, and we will need that in a couple minutes after we set up our ICE chart. So I have an ICE chart ready to go here. You'll notice that this equation is already balanced. So one of the first things you need to do if you do not have a balanced equation is you need to get your equation balanced in order to properly set up the ICE chart and the equilibrium expression itself, because we have to deal with exponential factors if there are any coefficients that are going to be greater than 1. So based on the problem, the initial concentration for the carbon monoxide and the water are 0.110 molarity. So I'll go ahead and I will fill that in on my ICE chart here, 0.110 and 0.110 here. Now, because this is the initiation of the reaction, I would not expect any of the products to have formed, so both of those would have a concentration of 0, just like we've seen in our other problems that we've practiced. Now the change here is going to be some amount that we lose that we will call X. So we're going to lose some amount of carbon monoxide, we'll lose some amount of water vapor, and then we will gain some amount of carbon dioxide that we call X, and we'll gain some amount of hydrogen gas that we call X. Again, just as a brief reminder, and you can go back and look at some of the other problems and the main video explaining this, if you have coefficients here, the coefficients, the stoichiometric coefficients, will be a multiplier to your X. So let's say that I had 3 moles of CO2 that were produced, then it would be 3X instead of X here. Okay, so then for the equilibrium part of the ICE chart, I simply express this as the initial and then the change as the final equilibrium. So I have some initial amount that is 0.110, and I will lose some amount X on the way to equilibrium. Same thing for the water vapor. I have an initial concentration of 0.110. I'll lose some amount X, and then 0 plus X is just X, and 0 plus X is just X. So once we solve for X, in this particular problem, we have already solved for the molarity of carbon dioxide and hydrogen gas at equilibrium. And then whatever that X value is, if I take the difference of that from the 0.110, that will tell me the molarity for the actual reactants at that point when we hit KEQ, when we're at equilibrium. Okay, so now we are going to set up the actual expression. Remember that KEQ equals the equilibrium expression, and in this problem, KEQ was 102. So I can state that 102 is going to be equal to the products over the reactants raised to their respective coefficients. Now, the coefficients here are all 1, so I can drop that out, and I don't need to worry about it in this case. So what do I have? I have X and X for the products. So I express the carbon dioxide as X, and I also express the hydrogen gas as X. Now, as far as the reactants are concerned, I have two of them, both of which are expressed as 0.110 minus X. And there's two of those, so that value is going to be squared. And to simplify this up here, X times X is simply going to be X squared. So what I really have is X squared over 0.110 minus X, and that term is squared. So again, the main point of the square root method is that if you have a square on the top and the bottom, you can simplify this entire expression by taking the square root of this side, and then you can take the square root of whatever the KEQ is. And so that will return a simplified version of the equation to you. So what would we get in a case like this? Well, the square root of 102, if you put that into your calculator, and I do encourage you to get out a calculator and follow along here, okay, is going to be 10.1. So it's almost 10 because the square root of 100 would be 10. Okay, and that is going to be equal to, now the squared term will drop out, so it's going to be equal to X over, and the squared term will drop out in the bottom, so it's going to be 0.110 minus X. So this is the simplified version after we have utilized the square root method, and we'll continue from there. So the next thing that we want to do to simplify this is to multiply each side by that denominator so we can start consolidating X into one side of the equation. Okay, so that's going to be gone. Now I'm going to need to apply that to the other side, the 10.1. And so what that would look like here is I would have 10.1 that's going to need to be multiplied and distributed to 0.110 minus X, right? And then that's going to be equal to the 10, I'm sorry, not the 10.1, the X, right? Because the X squared dropped out. So if I've got that there, then I can start solving for this. I'm going to need to distribute the 10.1 to the 1.110, and then I'll also distribute the 10.1 to the negative X here. Okay, so what does that simplify into? Well, once you distribute that and you work with everything, you should get 1.11 minus 10.1x is equal to X. And so in order to combine the X terms, I'm going to need to add 10.1x to each side. That will get rid of it on the left-hand side. And so this becomes X plus 10.1x. So there's an implied 1 in front of this X. So if I combine that together, it's going to be 11.1x. And so what I can simplify this to now is 1.11 equals 11.1x. So a lot of ones here that are going to come together. Now I can finally solve for x by taking 11.1 and dividing it on each side. That's going to drop this term out to just give me x. And then I will divide the 1.11 by 11.1. And so I find that once I solve for this, 1.11 divided by 11.1 is going to give me an x that is equal to 0.1. And I'm adding 0, 0 here just in terms of significant figures. Okay, so there's the x value. Again, remember, you're not done until you go back up and you solve for the actual equilibrium concentration. Now, when we are at equilibrium, the products themselves are just going to be equal to x as far as their molarity. So that task is already completed. But then I need to take the 0.110 minus 0.1 because that's what we determined x is. Okay, so to wrap this up, what we're going to do is we're going to say the carbon monoxide and the water vapor, because they have the same expression at equilibrium as far as x is concerned, are going to be equal to the following, which is 0.110 minus 0.100. And so that will give us 0.010 molarity for the concentration of the reactants. And then again, the CO2 as well as the hydrogen gas are both expressed the same way at equilibrium, and they're simply expressed as X. And so that means whatever the X value was, in this case it's 0.100 molarity, is going to be the answer for those. So hopefully this helps you further understand the square root method. You've seen some practice. Again, go back through the equilibrium playlist. You can check the link down in the description box below if you need additional help. But other than that, that wraps up today's lecture regarding the square root method. And again, we're going to move on to quadratics next time. So thank you so much for choosing to learn with Chem Complete. You can head on over to chemcomplete.com, where we have lots of free resources to help you. And there are also very affordable paid-for guides that walk through difficult content for only a couple of dollars. It's a great way to help support the channel. Other than that, thank you so much. Remember to hit the like button if you found this useful. If you comment, I'll get back to you as soon as possible. And remember to subscribe so you can stay up to date during your semester studies with anything chemistry related. Have a great one, and I will see everybody in the next lecture.